Okay, we're going to look at the sum of an arithmetic sequence. Notation for that is S subscript n. So if you're summing the first n terms of your arithmetic sequence, you can use that subscript. You don't see it used all the time, but it will be in places. If you sum a sequence, you get a series. So just that's your terminology. Summing a sequence gives a series. So this is an example of an arithmetic series. So I get a bit carried away with that. Right, let me move this board from underneath. Right, I'm going to do this with numbers to start with, and then we'll do it with algebra. So if I write down this sum backwards, so I get 27 plus 21 plus 15 plus 9 plus 3 is equal to S. So I would normally get you to do this in class, but it's a bit tricky at the moment. And then if I call this one equation 1, this one 2, and then we can do 1 plus 2. So 27 plus 3 is 30, 21 plus 9, 30, plus 30, plus 30 plus 30 is equal to 2 lots of S. So 5 times 30 is equal to 2S. If you look at what's going on here, the number of terms in my series is 5. And this 30 you can get from adding the first term and the last term, which I'm going to call L. It does get called L, by the way. And so from there, S is equal to a half lots of 5 times 30. And if you think about what's happening in terms of letters, 5 is the N and 30 is your first term plus your last term. So we can now sort of generalise that into a proper proof. This proof is examinable. So there's not many that are. It's not my favourite proof. I think it's a little bit boring. You just need to be able to regurgitate it. But it comes up every now and then. And it's worth about 4 marks when it does. So you should know this. It's one of the few proofs you need to memorise, to be fair. So I'm going to do exactly the same thing. We're proving the formula for the sum of an arithmetic sequence or an arithmetic series. The first term is A. The second term will be A plus D. The third term, A plus 2D. And then that continues until you get to your last term, which is your nth term. And that's equal to A plus n minus 1D. And you know that from the formula we did in our first lesson. So the nth term is A plus n minus 1D. And then we need to write the sum out again, but backwards. These brackets, they're not doing anything apart from separating out the terms. You don't, do you need them? You might not really need them, but I think they're quite nice to put in because they just make it really clear. So that's your nth term. The next one down will be A plus n minus 2d, because you'll have added d on one time less. And then we're going down to a plus d, and then plus a at the end. And then when you add them together, so we add these together. So when you do your first term plus your last term, you get 2a plus n minus 1d. And then moving along, so that's those two added together. Moving along and adding those two together, you're going to get the same thing each time. We saw that with the numbers. So a plus a is 2a, and n minus 2d plus d is n minus 1d. And then it starts getting a bit boring. So that's going to happen n times, because there's n terms in the series. And so 2s is equal to n lots of 2a plus n minus 1d. And then dividing by 2 or timesing by a half, you get a half n lots of 2a plus n minus 1d. And that's the formula you need to prove. The other formulae for the sum of the terms, which is useful sometimes, if you know the first term and the last term, you can do a half n a plus l. So you need to know both of those, but they are in the formula book. At least that one is. That one possibly isn't, actually. I'm not sure without looking. I'll let you look if you feel like it. But you need to be able to write out this proof if necessary in your exam. So it is an examinable proof.